Hi, I'm David Joseph. I'm going to talk about forecasting air quality in Beijing, China. So first, we'll set up the project and why people will be interested in this. So there were over a million deaths due to air pollution in China in 2015, and so policymakers need to implement smarter energy policies using forecasting, and they need to better distribute those masks as well to keep people from dying. And this time series forecasting is commonly used to help the governments in cities where there's a lot of pollution. And so we're going to make 72-hour ahead forecast, which is standard for this field. And let's go ahead and do some EDA. So first things first, looking at the scatter plot, we see that there is a clear seasonality in our data. There's probably multiple seasonalities because we're sampled at an hourly rate. The ACF suggests a wandering trend, but likely this is just due to the long seasonality. And this could just be a high order AR model. So then looking at the parser window, it tells us the same thing. And actually, if you sample this data at a weekly rate, you actually see a little hump right here, which indicates a long-term trend, such as maybe a yearly trend. So we resampled our data to daily, weekly, monthly, and quarterly data and plotted each year on top of each other to get an idea of the different trends. And we see here that there's a pretty clear yearly seasonality, and there's a lot of complex stuff going on here. So we might want to think about looking at multiple seasonalities. So then we looked at covariate, which we use categorical variables of daytime or nighttime because those were different. And then we use continuous variables of temperature, humidity, pressure, and wind speed. And these are all time series. Our final model included regression with autocorrelated errors, vector autoregression, TBAT, a neural network, and a long short-term memory recurrent neural net. And they are all combined using the stochastic gradient boosting machine, which is, again, a cutting edge and new standard for ensembling models. So our ARUMA model, which was not appropriate, we couldn't transform our series to stationarity. There was, again, this strong heteroscedasticity in our transform series. It failed all the long box tests. Our best model, we had a seasonality of 7 days with an AR order of 6. And surprisingly, it captured the scale of the time series real and was a pretty good forecast at an AC of about 18,000, but I'm worried this is chance or overfitting. Then we did regression with Fourier series regressors and autocorrelated errors, and the errors were correlated at AR5. And this actually did a pretty good job too. It didn't explain the scale, but it did a really good job at the lower points of our data set. This had an AAC of about 18,000. We did TBAT as well, which is basically the same way of representing seasonality with Fourier series, and but then it exponentially smooths the rest. And this performed pretty poorly. It had an AC of about 22,000. Then we use vector autoregression, which suggests that there's a complex relationship between all our variables, which we see here in these cross-correlation plots. And this did a pretty good job and picked up on a lot of subtle trends, such as here and here and here and here. And it performed with an AC of about 90,000. We did a neural net, which did about the same as the vector autoregression. Then we did a long short-term memory model, which was consisted of a time-forward LSTM, a bidirectional LSTM, and another bidirectional LSTM, and then they were recombined using a neural network. And this had an astoundingly good forecast with an AAC of about 15,000. And we calculated the prediction interval using recurrent dropout, and we trained our model using rolling time windows. So then we ensembled them all together, and on the right you can see a plot of each of our time series, and we see here that ARUMA was probably overfit or something was wrong because it was way off our black test set, while our neural network, or along LSTM, performed brilliantly here too in turquoise. And stochastic gradient boosting agreed that the ARUMA was not appropriate, and by combining them all, we produce an astoundingly good forecast with an ASU of about 5,400. And we calculated the prediction intervals by bootstrapping the residuals. Then we forecasted each of our 6 models 72 hours ahead. We explained the exogenous variables using VAR, and we scaled the LSTM using ARUMA, and then we boosted them all together to get this final forecast. For next steps, we want to include other cities in our model and expand our forecasting region. And we might want to deploy this model and make it dynamic so it retrains every time it gets new data.